Calculating the volume of a three-dimensional solid created by rotating a two-dimensional area around an axis is a fundamental challenge in calculus. Whether we are designing a mechanical part or calculating the capacity of a vessel, we need a systematic way to turn functions into volumes. Today, we compare the two primary tools for this task, the shell and washer methods. You might wonder why we need two different methods to find the same volume. The choice usually depends on which variable is easier to integrate or the shape of the boundaries. Sometimes one method leads to a simple integral, while the other results in a complex nightmare. Understanding both allows you to choose the path of least resistance. Before we dive in, ensure you are comfortable with definite integrals and basic geometric formulas. We will be summing up infinite to slices, fourth layers, so understanding how to set up an integral and knowing the surface area of a cylinder or the area of a circle is essential for building our volume formulas. The washer method is an extension of the disk method. We use it when the solid has a hole in the middle. Think of it as taking a large circular disk and cutting out a smaller circular hole. The area of this cross-section is the area of the outer circle minus the area of the inner circle. When we rotate around the x-axis, we stack these washers along the x-axis. Each washer has a tiny thickness, dx. By integrating from the start point A to the end points B, we sum the volumes of all these thin washers to find the total volume of the solid of revolution. The shell method takes a different approach. Instead of slices perpendicular to the axis, we use thin cylindrical layers parallel to the axis. Imagine an onion. As you peel each layer, you have a thin sheet. If you unroll that sheet, it becomes a rectangular prism with a volume of circumference times height times thickness. For a rotation around the y-axis using vertical shells, the radius is simply the x distance from the axis, and the height is the function value f, x. We integrate these shells from the inner radius to the outer radius. This method is often superior when the function is defined in terms of x but rotated around a vertical axis. The most important rule to remember is the orientation of your representative rectangle. In the washer method, the rectangle is perpendicular to the axis of rotation. In the shell method, the rectangle is parallel to the axis of rotation. This distinction determines whether you integrate with respect to x or y. Let's find the volume of the region bounded by y equals square root of x and y equals x squared, rotated around the x-axis. Since we are rotating around a horizontal axis and using washers, our rectangles are vertical, meaning we integrate with respect to x. Our outer radius is the top curve, and the inner radius is the bottom curve. We set up the integral from 0 to 1, which are the intersection points. Squaring the radii gives us x and x to the fourth. After integrating, we evaluate at the boundaries. The calculation yields a final volume of 3 pi/10 cubic units. Notice how the washer setup directly follows the outer minus inner logic. Now, let's rotate that same region around the y-axis using the shell method. Our shells are vertical, parallel to the y-axis. The radius of a shell at any point x is just x. The height of the shell is the difference between the functions square root of x minus x squared. Distributing the x gives us x to the 3/2 minus x cubed. We integrate from 0 to 1. Interestingly, we get the same result, 3 pi/10. This confirms that both methods are valid. The choice simply depends on which axis you are rotating around and which variable is easier to use. Sometimes, one method is practically impossible. Consider rotating y equals sine of x squared around the y-axis. To use washers, you'd have to solve for x, resulting in a messy square root of an arcsine. That is a nightmare to integrate. This is where the shell method shines. By using the shell method, we keep the function in terms of x. The integral becomes 2 pi times the integral of x sine x squared. This is a simple U substitution problem. By choosing shells, we turned an impossible integration task into a straightforward Calculus 1 exercise. What if the axis isn't the x or y axis? If we rotate around x equals -1 using shells, the radius is no longer just x. It is the distance from the axis to the shell, which is x minus -1, or x plus 1. Always draw a diagram to identify the correct radius. Similarly, for the washer method around y equals 5, the radii are the distances from the line y equals 5 to the curves. If the curves are below the line, the radius is 5 minus the function value. There's top minus bottom board right minus left logic from area problems applies here to find these distances. A common mistake is using the wrong variable of integration. Remember, for washers, the thickness is along the axis of rotation. For shells, the thickness is perpendicular to the axis of rotation. If you are rotating around the x-axis, washers use dx, but shells would use dy. In the washer method, students often subtract the functions and then square the result. This is incorrect. You must square the outer radius and the inner radius separately before subtracting. Geometrically, you are subtracting the area of the small circle from the large circle, not squaring the difference in radii. In the shell method, don't confuse the radius with the height. The height is determined by the function's boundary, while the radius is the distance from your slice to the axis of rotation. If you're rotating around the y-axis, the radius is usually just x. To choose a strategy, first look at your boundary equations. If they are all y equals something and easy to integrate, and you're rotating around the x-axis, washers are your best friend. If you're rotating around the y-axis but can't easily solve for x, shells are the way to go. Let's summarize. The washer method uses slices perpendicular to the axis, resulting in a pi r squared setup. The shell method uses layers parallel to the axis, resulting in a 2rh setup. One use is area of circles, the other use is surface area of cylinders. If you ever get stuck, just draw a single representative rectangle in your 2D area. Rotate that one rectangle in your mind. Does it form a flat disk or a tall hollow pipe? That mental image will tell you exactly which formula to use every time. Time for a quick check. If you have the function y equals x cubed and you want to rotate the region around the y-axis, which method is more direct? Think about whether you want to solve for x to use dy, or keep it as x cubed and use dx. The shell method is easier here. By using shells, you can integrate with respect to x, meaning you don't have to convert the function to the cube root of y. It keeps the math simple and reduces the chance of algebraic errors. Mastering volumes of revolution is all about practice and visualization. By identifying the axis, choosing the right representative rectangle, and setting up your radii correctly, you can solve even the most complex volume problems. Keep practicing, and soon these methods will become second nature. Generated by Vision Solve AI.